good morning. I would like to welcome you to this talk, to this TEWI-Kolloquium by Josef Teichmann. Josef is Corinthian.
Yes, a rare pleasure.
Studied at the University of Graz and was then in Vienna at the University of Vienna and at the Technical University of Vienna before he became a professor at ETH Zurich. Josef is very, very well known in financial mathematics, in stochastics, and all the surrounding fields. Nowadays, he does a lot of machine learning with his co-authors who also become well known because they do great work. And I don't want to spend too many words myself, so I would like to hand over to Josef. Thanks for coming.
Thanks a lot. It's a rare and particular pleasure to speak close to the place where I grew up. This is Obertrauburg in Oberkärnten. It's not the closest talk I gave. I gave once a talk in Villach, which was even closer to that place. Thanks for the kind introduction, Michaela, a former colleague from ETH, where we met and shared the same floor and discussed from time to time. And we also share a passion for stochastic differential equations and numerics of stochastic differential equation, which was one of the topic I was interested in for some time. More recently, we became very much interested in machine learning technology applied to questions of finance, of financial industry. And I would like to talk today about a particular aspect of this technology. These are so-called randomized networks in the realm of certain problems from financial industry. And I will in particular show about randomized recurrent networks, mathematical result which explains why they appear to be feature selectors of interest for decision-making processes. Good, let's try whether the technology works. Yes. So in financial industry, in insurance industry, it is apparently of high importance to gain quantitative understanding in dynamic decision-making. And the classical approach, which has been a theme through the 20th century, is the approach of modeling in by means of very often differential equations or stochastic differential equations, following a certain paradigm, which often is addressed as Occam's razor. Occam's razor means that you write models which depend on as few as possible parameters in order to achieve a certain task. And then after having chosen such a model, after having calibrated this model to data, you solve optimization problems or more complicated, maybe game problems on those models. Think, for instance, most prominently in the world of finance, the Black-Scholes model. As I said, given in terms of stochastic differential equation, and depending on two parameters, one is the market return, the other one is the volatility of the market. You have this typical exponential structure, which we also know from classical interest rate modeling. Additionally, you need to know today's price as 0, and then you have a stochastic process model for the evolution of a price of an asset. And one typical question which has been solved almost 50 years ago by Black and Scholes is the question how to price certain nonlinear derivatives in this market. And the result is by this famous no arbitrage argument that there exists a unique price for derivatives. Derivatives are just contracts whose payout is a random variable depending on the future development of this price. And the no arbitrage argument gives in a unique way by solving a certain optimization problem to price such derivative contracts. And coming back to Occam's razor, you see the model depends on two parameters. And if you leave one of the two parameters away, you really have a considerably simpler model and can solve less tasks with it. So that's somehow a minimal representation of a market which has on the one hand this noisy behavior around an exponentially growing quantity S. So that's a typical example of how Occam's razor is applied. And additionally, you have in those models usually that you can interpret the parameters by some hermeneutics. You can explain what the parameters mean. So this is a trend of the market. This is a volatility of the market. You have the initial price. So you have a very clear meaning what the parameters mean. In contrast to this classical approach, which has been immensely successful in all areas of technology, in economics, in physics, since Newton, such differential equation models have been of high success. Machine learning, the recently very successful technology, takes a completely different approach. It's against all good habits from this modeling approach. First, when you look in recent papers, you can read about so-called neural stochastic differential equations, or sometimes with a slightly different paradigm, signature stochastic differential equations. In those models, you do not have three parameters as in the Black-Scholes model. You actually have a highly overparameterized function family, which on the same data is calibrated. And instead of the few parameters before, you have these many parameters where each single parameter does not have a particular meaning. And also for different instances, when you use this model, the parameters also have different values. Still, they achieve a similar task as this model which we have here. So it is considerably more task or performance oriented already on this level of modeling or model choice. And then when you solve the optimization problem, again, you start with a highly overparameterized family of strategies, of decisions, use the same principle as here, and obtain by so-called training procedures prices and also strategies how to do risk management. So the result is the same. Again, it's performance oriented, but the paradigm is completely different. The parameters which you have in these highly overparameterized function families do not have a particular meaning anymore. You cannot call them drift or volatility, the single parameters of the model. And even if you run the model different times, you see that you have completely different choices of parameters. One instance of this is a paper which we published a couple of years ago together with colleagues from JP Morgan in London. It's deep hedging, where precisely this approach is in a certain market environment realized and shown to actually perform very well when it comes to questions of risk management which appear in financial industry every day. And what is this machine learning approach relying on? On the one hand, you have these overparameterized families of functions, which are often of a so-called neural network type. So they come with different architectures, feed-forward networks, recurrent neural networks, LSTMs. As I said already, neural stochastic differential equations, which is a sort of continuous time recurrent neural network, or signature-based models, signature-based stochastic differential equations, and training procedures on data. So you can imagine it like that you have a certain family of functions which replaces the vector field here and here, which is coming with many parameters, and then you have, given the tasks you would like to achieve, what you would like to reach as an objective, you have training procedures which tell you how to choose the parameters of those vector fields. Also, a fascinating aspect is that these training procedures usually remain somehow enigmatic, in the sense that one is writing down a problem and applies a certain algorithm how to solve that problem, but usually the algorithm is early stopped, so appears as a search of parameters in a very high-dimensional parameter space, and by no means you have a convergence result, and in particular not if you stop the algorithm so early. And therefore, actually, the problem which you solve to reach minima of certain objective functions can actually not be solved by the way the algorithm is applied. So it is sometimes not even clear which type of optimization problem is actually solved by the algorithms which are applied. And training procedures mean very often that you do not only choose parameters of a previously chosen family of functions, sometimes you also choose this family of functions. This is called choosing architectures. You train the hyperparameters. And in a way, you would say all good habits of classical modeling are left behind. You don't have convergence rate. You have overparameterization. You do not use sophisticated training algorithms. And sometimes also the objective, as I said before, which you try to reach, is certainly not solved by the algorithms which you apply. So in contrast, just to put this a little bit in perspective, to classical modeling where you have a very precise numerical technology, you have convergence rates, you have models with well-defined, meaningful parameters and small amounts of parameters. In machine learning, you leave all those good habits behind. You have many parameters. They are different each time you run the training procedures. Again, the training procedures do not really solve the problems you write down, and many aspects are actually of an enigmatic nature. The reason why we still use this technology and why we use it more and more often is the results are actually often very fascinating and far-reaching. I mean, when you look into the technological news in the last 10 years, you certainly remember, for instance, when the Go World Champion was first time beaten by machine learning technology, which is just an artificial board game player, and the board game player who does not rely on human knowledge and just calculating quicker than human beings. It is a board game player, an artificial board game player who learns to play the game on a high level by playing with herself. This self-play approach just giving the rules of the game to the player is something which is the basis of these reinforcement learning, machine learning technologies. And it is absolutely fascinating to see that this actually reaches superhuman performance. And this is one of the examples. You can see many examples. And last but not least, also that deep hedging, this technology, which I mentioned before, that this is actually used now in banks instead of Black-Scholes modeling or modeling approaches. These approaches against all good habits are actually used in production in order to do risk management tasks. And one of the reasons, in particular from the point of view of banking, but not only, is actually this robustness which you see there. Robustness in the following sense. So I remember when we started to do this deep hedging at JP Morgan in London, what fascinates the practitioners most is actually, in order to solve a risk management problem in a real market environment where you have market impact of your decision making, where you have transaction costs, where you have liquidity constraints, where the model might change over time. In order to do that, you just need to add or change 2 or 3 lines of code. Whereas in classical financial modeling, when you look, Black-Scholes theory relies on many idealizations and a very particular model. Already if you add transaction costs to Black-Scholes, you know these are these papers from the beginning of the 90s. Michaela is nodding her head. These are papers 70, 80 pages long, where you have a very precise analysis, but you need also this analysis to do it. So it's a very complicated problem of a completely different level of difficulty, only when transaction costs are added. In the machine learning setting, this is just one additional line of code which goes into the objective, and the method runs just the same way. You could argue, ironically, that not even in the ideal case you know why it works, and it works out of some reason, and in the case where you have transaction cost, it works again, but still it remains enigmatic. But I want to point out this robustness is something which drives the fascination for this technology. And well, just recently we had this paper, Deep Optimal Stopping, where you also can do optimal stopping problems in dimensions or in market environments where, from a classical point of view, was unimaginable a couple of years ago. So you can really do optimal stopping problems in S&P 500, and you can do them in a non-Markovian environment. And additionally, with transaction costs, we have never seen solutions of those problems with classical technology, because from this classical numerical paradigm, these are problems which lead out of complexity which you could deal with easily. And one aspect which, of course, us mathematicians is interesting is to achieve more insight into this enigmatic procedure of training and model selection, while leaving behind all these good habits from classical modeling actually is something reasonable, and this comes to this question of provability. So why do these artificial traders work so well, and how can we gain a quantitative understanding into this? Many people in machine learning and computer science, but also in mathematical finance, work on this question. And what I show here is a very particular aspect of it. I would like to emphasize the point that so-called randomized networks, so these are neural networks I will define later, but which come with with a large amount of parameters which are actually only randomly chosen and never trained, why those randomized networks actually might provide good models for, on the one hand, provable techniques, and on the other hand, even for production questions, for instance, when it comes to this optimal stopping problem, you can really see that already those randomized networks perform almost as well as fully trained networks. So this is one aspect which one can see. Other aspects are really analyzing what this early stopped training procedure means, and I'm happy that Hanna is here now, one of my PhD students, also from Klagenfurt or Carinthia. And she, together with another PhD student of mine at ETH, Jakob Heiss, they are working strongly on understanding better how these early stopped training procedures, which problem they actually solve, and why this is of interest. But this is highly delicate functional or numerical analysis. I will not go into this direction today. I just say there are different ways how you can analyze or attack this type of problem, and the approach I choose today is just to understand randomized networks as a rough model for what might be a result of early stopped training, and also to show in one particular case, namely in the case not of feed-forward networks but of recurrent neural networks, that there are proofs why randomized networks actually have very good feature extraction properties. And it is, of course, of interest also from a point of view of sustainability of these learning technologies, that to see these randomized networks not only have a small amount of parameters which have to be trained, additionally, and you can prove that you can approximate certain tasks by them, but you can also interpret this smaller training complexity as something which increases the sustainability of these models. Usually, machine learning technology is quite energy intensive. You need a lot of energy to do training of huge networks, and randomized networks decrease this training complexity tremendously by often not losing accuracy. So that's also an interesting aspect. And an aspect which is also scientifically interesting, one of the big questions in computer science is, or in neuroscience is, how does actually this low energy consuming computer which each of us is carrying around our brain work? And what one can definitively say, it does not work like a von Neumann computer in the sense of energy consumption. Okay, let me come to one aspect now which goes closer to the mathematical theory I'm going to present. So I'm going to talk about recurrent neural networks and the question why recurrent neural networks might be as well replaced by randomized recurrent neural networks without losing accuracy of task performance. So first, how can you imagine a recurrent neural network for the most of us here, mathematicians? The easiest way to think about it is just to think of so-called controlled ordinary differential equation. So imagine a so-called control. So this is a curve taking values in some space Rd. Take it, let's say, C infinity, so a nice smooth curve. And then imagine some space Rn, where you run a non-autonomous differential equation driven by d vector fields in the following way. So the movement of this particle in Rn is with a speed which is coming from vector fields depending on the point where the particles are, d vector fields, and you take a superposition of these speeds by the derivatives of the control u. You can imagine by choosing the control, you switch on different speed vector fields and you can go in certain directions depending on how those speed vector fields are chosen. This is a controlled ordinary differential equation. If now you choose the vector fields vi as neural networks, so a neural network is nothing else than compositions of affine functions on Rn with one type of nonlinearity, and you can do that more often. Then you increase the so-called depth of the network, or you can do it only once, then you have a shallow network. So solving such a type of controlled ordinary differential equation leads to a recurrent neural network in the sense that you are interested in the map from the control to the solution of the equation. And very often you are not interested necessarily in the solution, but you're interested in a map of the solution to some other space. And this is an additional regression which is considered. So this you can see a recurrent neural network, a fully trainable recurrent neural network trains all the parameters of these vector fields together with this so-called readout map W. And a randomized recurrent neural network actually does not train those vector fields, but chooses those vector fields randomly, in the sense that the affine maps which appear in these vector fields are chosen according to some distribution and randomly chosen once and remain untrained. The only trained aspect is this W here. And the question, which is a little bit surprising, is the following. Does a randomized recurrent network, where you choose this randomly and you only train the W, achieve a similar performance as a fully trained network, where you actually also choose the parameters of those vector fields according to the task you would like to achieve? And from a mathematical point of view, I remember when I heard it first time, it seems absolutely obvious that, of course, when you train those parameters additionally, you have more degrees of freedom, and therefore you should achieve certainly better performance than when you only train the W. But, and I come a little bit again to history, these randomized networks appear already since 20 years or more in a field, an old field of computer science called reservoir computing. Reservoir computing is a field where random dynamical systems, so precisely when you choose those vector fields here random and you have a moderately high dimensional space here, so n could be in the 100s. When you choose them random, they call such fields then such dynamical systems, random dynamical systems, they call them reservoirs. Choosing them random and considering just learning this map W here, that this actually very often is an excellent way how to approximate generic dynamics. So this is something which, when you hear it first time or see it first time, it is something absolutely fascinating, but it has been proven in many contexts that this is a procedure which works well, and this is one of the reasons why this funny idea that randomized recurrent networks actually have a similar performance as fully trained ones could be pursued. You have a question?
Yes. Just for my understanding, what does the mu have to do with
The U.
Oh, it's a U.
I'm so sorry. Yeah. It's the same. Both is a U. Is it okay?
Yeah.
Yeah. So the idea of reservoir computing is precisely this idea of randomized recurrent networks, and they have been used in order to approximate generic, usually chaotic dynamical systems with actually high success. So when you look a little bit into this literature, which has been founded by Herbert Jäger about 20 years ago, you see very specific chaotic dynamical systems which are observed, and then one trains such a readout matrix W on a random dynamical system and achieves excellent prediction qualities of this procedure. This is the field of reservoir computing. Right. What is also fascinating in reservoir computing often, and this brings me a little bit back to this theme which I alluded to before, often those solutions of these randomized or these random differential equations, they are not calculated on computers, but they are calculated by physical experiments. So they are physically realized, not realized on von Neumann computers. You do certain experiments where you feed in these controls U, and the experiment realizes this type of equation, and you just measure this output. For instance, there are optical computers which work with this principle. And as I said, the main paradigm is just that you have this split of, let me make it here. You have U. This is a dynamic you would like to learn going to Y. And you split this into the reservoir. And the only thing you train is this regression matrix W. You split this input-output map in a generic part, which is the reservoir. This is this random dynamical system, and the readout part. Yeah. And often this readout part is something linear. I could show, if it were my computer, some examples where you see this very impressively working, but I just recommend take a look on my webpage. There's the lecture Machine Learning in Finance, and there you can see some code examples where this works. And well, let us now analyze this question a little bit in a more familiar context, in a context of not controlled differential equations, or actually controlled differential equations, but the control is now not a C-infinity function, but just a Brownian motion. So we are interested in understanding the map from an input noise to a solution trajectory of some a certain given dynamical system, and we would like to understand whether this procedure can work, that we are trying to construct a reservoir and just learn a certain linear regression. When you look at the problem like that, you would say this sounds really funny, that with a random dynamical system, which has no information about that, it is possible to approximate such a given dynamical system well. Let me give you some arguments for that, and I skip a little bit over this here, and let me just take this in this mathematical context here. So we have this controlled differential equation, U either a control or a Brownian motion or some semi-martingale as you like it. Can we understand this splitting procedure, and in particular the random aspect here, from a mathematical point of view? Yeah. And a first result, which one obtains by going a little bit into the theory of dynamical systems, is the following. When you take, now it gets a little bit algebraic, consider these controls U, and all iterated integrals of the different coordinates of the control with respect to itself. So these are sort of polynomials on the set of paths, of control paths. All iterated integrals. And we do collect them here in an algebraic way, in the sense that we are multiplying these numbers. So these are just these iterated integrals. We are multiplying them with monomials in some indeterminates. So this gives a formal power series. There's no statement about convergence set here. It's just a collection of all those iterated integrals. And when you look at this formal power series, you can, in this algebra of formal power series, just say this formal power series formed by the iterated integrals actually fulfills a differential equation, and the differential equation is just, if I take the derivative with respect to the upper variable t, it is as if I were multiplying the solution of this equation from the right with the corresponding EI, because this is precisely how it is defined, these formal power series of iterated integral coefficients. So we have now, seeing that, constructed on an infinite dimensional space, namely the space of this formal power series, a dynamical system, a bona fide fixed dynamical system, and this dynamical system just collects all iterated integrals in the controls. Now, when you look at this equation here, by a very simple iterative argument, let me maybe write it here. Yeah, let me write it just here. Just by the definition of this differential equation, you see that actually you can write just by the chain rule, take the derivative of the function applied at the YR in the direction of the vector field YR, and multiply that with the control here. So this is precisely for any test function the way how this differential equation is to be understood. Now you can give a name to this quantity here, as we usually do it in geometry. This is the transport operator associated to the vector field, right? And then you see test function applied on the solution gives a value plus an integral over another test function applied to the solution. You can iterate this equation, and what you get is an expansion with respect to the iterated integrals of the controls. And when you write that down, since we have now an algebraic way how to do that, you actually get this very nice Taylor expansion theorem. A test function applied to the solution of this controlled ordinary differential equation is a very particular map W, a linear map W applied on iterated integrals, and the remainder term, which is getting small with respect to the amount of time which is passing, and if t is smaller than 1, you get a approximation result. So what is here is just the transport operators applied to the test function, and here you have the iterated integrals. The iterated integrals we call signature, the collection of them, and these are iterated integrals up to depth m. Good. Now, from the point of view of reservoir computing, which I was alluding to before, actually, this is precisely what we have here. We have here some generic dynamics. We have a reservoir. This is the dynamical system consisting out of the collection of all iterated integrals. And we have a linear readout, which is reproducing this given dynamics. This is, of course, a well-known result since 50, 60 years. But it is not precisely what we had before. You remember in this paradigm of reservoir computing, the important aspect was actually that this dynamical system here is not a fixed dynamical system which produces a certain amount of polynomials which you need in order to approximate the generic dynamics, but it is a random dynamical system. The question is, why is this of a similar nature as this very well-defined and additionally infinite dimensional dynamic system? This is the mathematical question, and let me consider this now a little bit in depth. So we have this somehow formal reservoir computing result that you can write any dynamics as a linear readout of a very particular dynamics, an infinite dimensional one. We ask whether it is possible to replace this very particular dynamics of which creates all the iterated integrals, to replace it by a random dynamical system. And then we would be in the spirit of reservoir computing. And the path which we have been choosing here is this idea which goes back to an article from the 80s of two famous mathematicians. There's a very famous article, Johnson-Lindenstrauss theorem. It's a compression of information statement, and it's the following statement, very funny statement when you read it first time. So you give yourself a level of accuracy epsilon, and you give yourself an n-point set in some high-dimensional space Rn. You can think of Rn being some Hilbert space. The little n does actually not appear in the estimates. The important statement is that there is a linear map onto a space of dimension k, and k should be considered considerably lower dimensional. And this linear map has the property that actually it preserves the geometry of this n-point cloud. So this means that it is almost isometric, or Lipschitz with Lipschitz constant 1. For all points v1, v2 in the n-point cloud Q, you know that the distance of the image points fv1 and fv2 is almost the same as the distance of the arguments for all points in this n-point cloud. And the fascinating thing is, of course, how can you choose the dimension? How small can you choose it? And the result of Johnson-Lindenstrauss is actually you can choose it logarithmic in the number of points in Q, with some a denominator which depends on epsilon and which is actually a troublemaker in the proof which follows. But this is this Johnson-Lindenstrauss theorem. Interesting is also it's not only an existence result, it's a result which tells you how to construct in a probabilistic way this map. So it's not only that you have it, you also know that if you choose a random matrix with IID standard normal entries of size k times n and k of this type, then with high probability, 1 divided by square of k of this random matrix will satisfy this property. Not always, but with high probability it does this. This is the Johnson-Lindenstrauss theorem, and it tells you can mimic the geometry of an n-point cloud in a log n-dimensional space, at least asymptotically. That's in many respects fascinating news, and it's not what you tell your kids when you bring them to sleep in the evening, in the sense that that you have a 1,000 dimensional space and you have e to the power 1,000 almost orthogonal vectors there. A 1,000 dimensional space, e to the power 1,000 almost orthogonal vectors. This is what it says. But it's a fact of high dimensional geometry, and what is always nice about facts of this type, which are counterintuitive, it has additionally the property it's very easy to prove. So the proof is half a page, and it's actually some concentration of measure result, as you can imagine. It's a beautiful piece of mathematics to take a look at. And this is precisely what we apply to this here. So we have here a very specific dynamical system which produces all iterated integrals, and we apply to this guy here a Johnson-Lindenstrauss map in order to obtain something which is compressing the information and still working from the point of view of regression, but being considerably lower dimensional. And the result is then the following. Looks a little bit funny at that point, but let me just write it down. So this is joint work with Christa Cuchiero, Lukas Gonon, a former PhD student of mine. Christa is a professor in Vienna. Lyudmila Grigoryeva, who is in Warwick at the stats department. Juan-Pablo Ortega, who is in Singapore. And the result is the following. If you take your signature, so this is this collection of all iterated integrals, and if you consider a Johnson-Lindenstrauss map F from the collection of all iterated integrals up to order m into some Rk, and k will be related to the dimension of the algebra of formal power series up to order m, such as Johnson-Lindenstrauss map, and you order it in the following way. So you have here the adjoint and the f, and you have some coefficients. This gives you then a random dynamical system. Of course, the randomness is relatively complicated depending on the Johnson-Lindenstrauss map. Then solving a regression with respect to signature, which is just representing a generic dynamics, as we showed before. This is just a Taylor expansion theorem. Or solving a regression with respect to randomized signature. This is the solution of this guy here, is of this type. And of course, Michaela or all her students recognize immediately the way how such things are proved. These are very usual techniques in numerical analysis, where you have the initial value here, and here you have a sort of variation of constants argument, and the important guy is here the epsilon, making it small, and those two norms. Not going too much into detail what this precisely means. It just says that solving a regression with respect to this fixed dynamical system or solving a regression with respect to these random dynamical systems leads to similar results. If the dimension of the random dynamical system is chosen moderately low but not small, so this is logarithm of something which is exponential in the dimension d of the control. And when you look at a little bit more down to earth, you can say actually this X, this randomized signature, looks precisely like that. Choose some random matrix Mi, a random shift Bi, and solve this controlled equation. So this is now really a reservoir in the sense that you have a random dynamical system. Choose the dimension of X in the hundreds. So we are talking here of K somewhere in the hundreds. Then the previous result tells that the regression on those guys can represent up to a certain order of accuracy any dynamical system written by or driven by these controls UI. And here this now really deserves to be called a reservoir, and this is an actual proof why some types of recurrent neural networks which are randomized can approximate generic dynamics. Of course, there are many things which one can criticize here. So actually how this dynamics is chosen, that here you have a recurrent neural network with a very, very simple recurrent cell. So this is linear in X. Usually you would have here a nonlinearity. So this is a very simple, shallow network with a linear activation function, which usually is not allowed as an activation function. And there is no statement about, in this theorem here, what happens in the case which is interesting for reservoir computing, namely when the t gets large. So usually this is used for long-term predictions, reservoir computing. Here this proof does not make a statement about it. But after having criticized it on many levels, it still is a first proof which tells why random dynamical systems and classical dynamical systems which produce these Taylor bases, why such dynamical systems can produce similar results when it comes to regressions of given dynamics you're interested in. Okay, in order not to go too far beyond the patience of my host here, I just end by showing a little picture, which is a picture which you could also see in the simulations on my webpage. So here you see actually, maybe not particularly long, but still a prediction which is done for up to 4,000 time steps here. Green corresponds to a given dynamics driven by two Brownian motions of a Saber model, which you just observe. So you observe the Brownian motions, you observe the dynamics, the green dynamics, and then you are taking the Brownian motions, map them into the reservoir, which is just a random dynamical system, learn how to represent via regression matrix green by the reservoir, and then you can make predictions either into the future or just for a new Brownian motion, and this would here be a new Brownian motion where you just look how well this representation of this dynamics works. Of course, this is an interesting econometric model first, and let me end with that. This is one of the most recent works we are doing. It is just saying, take S&P 500, all the 500 prices you have of this index, the underlying prices there, and try to form a reservoir of the so-called market Brownian motion you can find behind this, these 500 prices. Make a regression of those prices on the reservoir, and then use these regression coefficients in order to write an econometric model, let's say, for pricing or prediction tasks. And in that sense, it's a high-dimensional and very versatile econometric model in this style of reservoir computing by representing features of these market Brownian motions by a randomized recurrent neural network. And this brings me back to the beginning of this talk, when you look how in classical modeling a dynamics was represented. You would say you have a certain stochastic differential equation where you know precisely what the coefficients or the vector fields mean, and you try to represent it as low dimensional as possible. Here the dynamics is represented through random matrices, where of course the random matrix does not have a particular meaning and a regression coefficient on this random dynamical system. So it's a completely different way how to represent the dynamics, but with the same outcome and same performance. And yeah, and as a last statement, one difference is, in contrast to classical modeling, this model, what I explained now, where you have a randomized recurrent network and then a regression task to solve, is from a computational point of view, of course, extremely easy to calibrate. It's just a regression which you have to solve. If you were solving a high-dimensional task of calibrating to a time series where you have vector fields depending on a couple of parameters, you would see a very complicated optimization problem which takes a long time to be done. Okay, I think I stop here, and yeah, it's not too late.
Thank you very much for the nice talk. Are there any questions by the audience? Ellen?
Can you go to this graph of the predictions at the end? I don't know if it works. Yes, so I was curious. For instance, I see that in the first graph, the prediction looks quite loyal, so to say, to the original one, to the real one. But in the second one, of course, at the end, it's a little bit this deviation from the...
Yeah.
So are you happy with this shifting? So it still gives you in practice a lot of information. I mean, the form, of course, the shape of the graph is quite close, but about the shifting values, are you happy with that at the end?
Let me say this has just an illustrative purpose. So this is neither something which is fully done. It is just showing that when you have a Brownian motion which is driving the green solution, and you calculate from the Brownian motion the reservoir, and you take the regression coefficients, which are in this case calculated up to here, then you can get some predictive power a little bit into the future. It is not perfect, so it illustrates that you have a time component there which is not yet completely understood how one could improve that, but it's just from an illustrative purpose how this works. So in that sense, no, I'm not happy with that, but I also don't really know how to improve that yet. Reservoir computing originally, as Herbert Jäger designed it, works here for long term, but for different dynamical systems. So they have an ergodicity, which here is not the case.